This presentation is a part of a lecture series on the C++ programming language by Michael Adams at the University of Victoria in Victoria, Canada. For those of you who might be interested, a copy of the slides for this lecture series can be downloaded from the website whose URL is given at the bottom of this slide. In this section of the lecture material, I'm going to give a brief overview of the vector class template from the standard library. The vector class template in the standard library provides a dynamically sized one-dimensional array type where the type of the array elements and the storage allocator used to allocate memory for the elements are specified by template parameters. So what I mean by dynamically sized is that you can add and remove elements from the vector as the program is running. The size of the array is not fixed. The declaration of the vector class is as shown here. It's a template. It has two template parameters. The first is denoted by t, and this corresponds to the type of the elements in the vector. So for example, if you want the vector to hold a bunch of elements of type int, then you would choose as the parameter t here the value int. The second parameter is an allocator, and as you can see it has a default value, which is the allocator from the standard library. In most applications you probably won't need to override the default. You only need to override the default if you want to do some sort of custom memory allocation. And in the following slides, I'm going to give an overview of the vector class. I won't cover every little detail, it's just an overview. For additional information beyond what I'm going to be talking about here, you can refer to the two links that are given at the bottom of the slide. The vector class has quite a number of member types, which I've listed on this slide. Some of these types are more commonly used in practice than others, and the ones that are sort of more commonly used I've highlighted in magenta to make them stand out on the slide. So if you go through each of the member types in order, value type is just a synonym for the type of the elements in the vector. In other words, your template parameter t, the first template parameter for the vector class. Allocator type is a nickname for the type of the allocator that's used to allocate memory for the elements in the class. In other words, this corresponds to your second template parameter for the class. Size type is an unsigned integral type used to measure size of things typically. For example, there's a member function called size that returns the number of elements in a vector. The return type of this function is size underscore type. Difference type is used to measure distance between elements in the vector. Because the distance is a signed quantity, it can't be the same as the size type. It's some signed integral type. Reference and const reference are just references and const references to value type. In other words, a reference and const reference to the elements actually in the vector. Pointer and const pointer are pointers that are returned by the allocator. Iterator and const iterator sort of go together. They're essentially a random access iterator type that can be used to access the elements in a vector. The only difference between iterator and a const iterator, the iterator type, you're allowed to change the object that the iterator refers to. In the case of the const iterator type, you're not allowed to modify the object that the const iterator refers to. So iterator and const iterator are similar to the idea of a pointer to something that's not const and a pointer to something that is const. We also have what's called a reverse iterator and a const reverse iterator. What a reverse iterator is, it's an iterator that iterates over things backwards. So in other words, when you say plus plus to go to the next one, really what it's doing is minus minus and going in the backwards order. Sometimes it's convenient to iterate over things in backwards order, so this is what a reverse iterator is used for. And the reverse iterator comes in two flavors. There's the reverse iterator and then there's a const reverse iterator. The only difference between these two is that a reverse iterator, you're allowed to modify the thing the iterator refers to. In the case of a const reverse iterator, you're not allowed to modify the thing the iterator refers to. In other words, reverse iterator is sort of like a pointer to something that's not const, whereas a const reverse iterator is like a pointer to something that is const. On this slide and the next few slides, I have a summary of the member functions for the vector class. So in terms of construction, destruction, and assignment, we have many different constructors for the vector class. In other words, the constructor is overloaded. There's many different ways that you can construct a vector. You have a destructor, assignment operators. Perhaps more interestingly, though, we have a bunch of functions which relate to iterators. So we have a member function called begin, which returns an iterator to the beginning of the vector. In other words, an iterator which refers to the first element in the vector. End returns an iterator which refers to one past the last element in the vector, which basically corresponds to the end of the vector. Then we have a few other pairs of functions. We have cbegin, cend, rbegin, rend, and crbegin and crend. All of these basically return iterators that refer to the beginning and end of the vector. Now, the begin meaning the first element in the vector, end meaning one past the last element in the vector. The only difference between these, the C in these function names, C begin and C end, stands for constant. So the iterator that's returned by C begin and C end is a const iterator. The R in R begin and R end stands for reverse iterator. So R begin and R end return reverse iterators for the beginning and end of the vector. And then in CR begin and CR end, the CR stands for const reverse. So CR begin and CR end return const reverse iterators that refer to the beginning and end of the vector. On this slide, we continue with the list of member functions for the vector class. The next group of functions that I want to talk about relate to the capacity of the vector. So the first member function is called empty. It returns a bool, in other words, true or false, to indicate whether the vector is empty. In other words, it has no elements in it. The next member function called size, it returns the number of elements that are currently in the vector. Max size returns what's the maximum number of elements that the vector could hold. Capacity returns how much storage there is that's been allocated for holding elements in the vector. The capacity is always at least as big as the size, because obviously there has to be enough memory allocated to the vector to be able to hold however many elements are currently in the vector. However, the capacity can be larger than the size. In other words, there may be more memory allocated for the vector than what's currently being used. And capacity returns this amount that's been allocated. Reserve allows you to request a change in the capacity. You can say, please make sure that there's enough space allocated for n elements, where n is a parameter passed into reserve. Shrink to fit basically forces the capacity of the vector to be equal to size. So in other words, if there's more memory allocated than you're actually using for the vector, it shrinks the amount of memory that's being used so that you're only actually using the exact amount that you need. In other words, the capacity is set equal to the size. The next group of functions relate to element access. The first is the subscripting operator square brackets. This allows you to gain access to a particular element in the vector with no bounds checking. So in other words, if the subscript that you provide is out of range, who knows what's going to happen, but nothing good. There's a member function called at, which does a similar thing as the subscripting operator. The only difference is that at does bounds checking. So if, for example, there's 5 elements in the vector and you give the index 10,000, which is clearly ridiculous to do because it's out of range, this will cause an exception to be thrown and your program will terminate, well, assuming that you don't catch the exception. Front and back are used to access the first and last element in the vector. They return references to those elements. And data returns a pointer to the start of the element data. Again, on this slide, we're continuing along with our list of member functions for the vector class. The next group of functions I want to talk about are modifiers. Essentially, they allow you to modify in some way a vector. The first member function is called clear. It just clears the contents of the vector by emptying it out. So after calling clear, the number of elements in the vector will be 0. The assign member function is used to assign one vector to another. The insert member function is used to insert an element into the vector. Emplace is similar to insert. It inserts an element, but what's different is that when it inserts the element, it constructs it in place inside the vector, whereas insert will copy the element into the vector. Emplace, instead, it creates the element that you want actually in the vector to begin with. Pushback adds an element to the end of the vector. Emplace back is, again, similar to pushback, but the difference is emplace back actually constructs the new element in place inside the vector, whereas with pushback, it actually copies it in. Erase erases an element from a vector. Pop back deletes the last element from the vector. Resize is used to change the size of the vector to a different size from its current size. And swap swaps the contents of two vectors. And then the last group of functions that we have here relate to allocators. There's a member function called getAllocator, which can be used to get the allocator that's used for memory allocation for the vector. When using a container class like the vector class, one has to be particularly careful about the invalidation of references, iterators, and pointers. And I'm going to elaborate about what I mean by this. Earlier we talked about the capacity of a vector. The capacity is just the total number of elements that the vector could hold without having to reallocate memory. In other words, it already has enough memory allocated to hold capacity number of elements. Now, any operation that causes memory to be reallocated, in other words, the chunk of memory that's being used to store the contents of the vector, anything that causes this chunk of memory to be reallocated, which means typically it's going to move to somewhere else in memory, will cause anything that's referring to the elements that are stored in that memory to be invalidated, meaning that all iterators, references, pointers that are referring to elements in the vector would become invalid if memory is reallocated. And essentially any operation that changes the capacity of a vector causes reallocation of memory. So you have to be particularly careful about operations that change the capacity of a vector, because any operations that change the capacity of a vector can invalidate references, iterators, and pointers. And for example, any operation that adds or deletes elements to or from a vector can have the potential impact of invalidating references, iterators, and pointers. And in particular, operations that can invalidate references, iterators, and pointers to elements in a vector include this list here: insert, erase, pushback, popback, emplace, emplaceback, resize, reserve, assign, assignment operator, assign, clear, shrink to fit, swap, basically quite a large number of functions. So you have to be very careful about this, because this issue can arise quite frequently if you're not careful. And it's not a big deal if you invalidate references, iterators, and pointers. Sometimes you have to do it because you have to use one of these operations. But the important thing is that when you do want to use one of these operations and you do cause references, iterators, and pointers to be invalidated, you have to be careful not to use them anymore. And the common bug is that you don't realize that you've invalidated one of these things, you keep using them, and then only bad things can happen in your code as a result. On this slide, I have an example to help illustrate in more concrete terms why it is that iterator invalidation can occur. In other words, why it is that certain operations can result in iterators or pointers or references that refer to elements in a vector to become invalidated. So in this example, we're going to consider a vector that has 3 elements in it, A, B, C. And we also have an iterator that's referring to the second element in the vector. So I is an iterator, and it's referring to the element B in the vector. Start here is just a pointer inside the vector class, the class object, that tells it where the vector starts, where the data for the vector starts in memory. So it's just a pointer to the very first element. This is not something that you see as a user of the class, but obviously the class itself, the class object, needs to keep track of where its data is actually stored in memory, otherwise it won't know how to access it. So this is what's denoted by this variable start. Now what we're going to do with this vector here, this vector has a capacity of 3, so it only has enough memory allocated to store 3 elements. It can't hold more than 3. Now what we're going to do is we're going to call pushback to push back or add to the end of the vector another element called D. When we go to do this, however, because the vector that we have doesn't have enough capacity to store a 4th element, there's only enough memory allocated to the vector to hold 3 elements, and we already have 3 elements there. In order to add another one to the end, what we have to do is we have to allocate an entirely new chunk of memory that's bigger, that's big enough to hold at least 4 elements. Then the vector class will copy these 3 elements, A, B, C, into this new chunk of memory over here. Now with this new chunk of memory, because it's bigger, it's big enough that I can put D at the end, so that it's big enough to hold a 4th element, so D gets stuck on at the end here. And then this start pointer that's inside the vector object that keeps track of where the data for that vector object is located in memory, it's updated to point to the first element in this new chunk of memory. Now the very last step that's done here, and this is the critical thing with respect to iterator invalidation, is because this block over here of memory is no longer used, because all this data has been copied to a new place in memory, and only this new chunk of memory is going to be used in the future by the vector object. Because of this chunk of memory gets deleted. It's all freed. So basically everything in this chunk of memory is gone. You don't know what's going to be there. At some later point, probably a new variable will be allocated in that memory and it will be reused for some other purpose. But the critical thing to note here is that the iterator I that we had that was pointing to or referring to the second element in our vector, after we've deleted this chunk of memory here, I is still pointing to the same location in memory, but this location in memory here is no longer used by the vector class. So in effect, what's happened here is that secretly behind the iterator's back, we've gone and completely moved in memory where the contents of the vector is stored, where the elements of the vector are stored, and it has no way of knowing that this move has taken place, that we've moved where things are in memory. So it's still pointing to the old location for B, but little does it know, really B is over here now. So this iterator has been invalidated in the sense that if you use it, it's going to be referring to the wrong place in memory, and only bad things are going to happen as a result. So again, you have to be very careful of iterator invalidation when you're using container classes like the vector class, because otherwise you could end up using an iterator that actually doesn't refer to anything. It refers to some random place in memory, which is not going to do anything good in your code. On this slide, I have some examples of creating vector variables to help illustrate some of the constructors that are available from the vector class. So the first example I have here, I'm creating a vector of doubles called v0. I'm not providing any parameters for the constructor here, so this will invoke the default constructor for the vector class. And as it turns out, the default constructor for the vector class simply creates an empty vector. In other words, it creates a vector that contains 0 elements. In the next example, I'm creating a vector of doubles called v1, and I'm providing a single parameter to the constructor. In this case, the constructor that it gets invoked is going to construct a vector that has this many elements in it, in other words, 10 elements. For a built-in type, which is what we have here, for a vector of a built-in type, the elements will be uninitialized. If this was a user-defined type, then these elements would be initialized with a default constructor. In the next example, we have a vector of doubles called v2, and I'm providing 2 parameters to the constructor in this case. The interpretation of these parameters, the first parameter is the number of elements in the vector, and the second parameter corresponds to the value to which to initialize each of the elements in the vector. So this is going to create a vector of doubles with 10 elements in it, and each of the elements is initialized to 5.0. Then in the last example here, I'm creating a vector of ints called v3. And notice I have brace brackets around these values that follow the v3. This is what's called an initializer list. And for the vector class, if you provide elements in an initializer list, what it will do is it will initialize the vector with the actual elements being the ones that are specified in the initializer list. So in other words, this will create a vector of ints where the elements are 1, 2, 3. So there will be 3 elements in the vector, and the elements are equal to 1, 2, and 3. On this slide, I have an example that makes use of iterators for the vector class. So if we look at the code example, we have this function main, and we're creating a vector of ints. So each of the elements in the vector has type int, and we're using the brace initializer, basically an initializer list, to initialize the vector. So this is going to create a vector v where the elements in the vector are 0, 1, 2, 3. So the vector has 4 elements, which are 0, 1, 2, 3. Then in the first loop that we have here, this is a range-based for loop. We're going to loop over each of the elements in v, and each time through the loop, I is going to be a reference or nickname because of the ampersand here. It will be a reference for the particular element in the vector that we're referring to, and we're going to increment it. So after this loop finishes, basically what will happen is instead of having 0, 1, 2, 3 in this array, we'll have 1, 2, 3, 4. In other words, each element will be incremented by 1. Then after this, in the second loop, we just print out the contents of the vector v. So we're looping over each element in v, and I corresponds to the particular element, and then we're just printing out I. So what this is going to output is 1, 2, 3, 4, because we've incremented each of the elements in the array before we printed them, so then now they're going to be 1, 2, 3, 4 instead of 0, 1, 2, 3. Then in the next loop that we have here, we're looping from begin to end. So begin returns an iterator, which is the first element in the vector, and refers to one past the last element in the vector. So we're going to start at the first element, loop until we go past the end, and each time through the loop we're going to increment the iterator so it moves to the next element in the vector. And what we're going to do is for each element, each iteration, we're going to dereference the iterator, which is going to give us access to the element that the iterator refers to, and then we're going to subtract 1 from it. So what this loop is going to do is it's going to decrement each of the elements in the vector by 1. Then in the next loop, what we do is we print out the contents of the vector, but we're going to do it in a little bit different way from what we did above. We're going to use cBegin and cEnd. We're going to use iterators instead of a range-based for loop. So we create our iterator I using auto, and we're getting the iterator from the member function cBegin. So this returns a const iterator, which refers to the very first element in the vector. And we're going to loop until we hit cEnd, which is 1 past the end. Each time through the loop, what we're going to do is we're just going to print out the value that the iterator refers to. In other words, we're going to dereference the iterator and print the value that's associated with it. After this, we print a new line character. So when we execute this loop, we're going to end up with 0, 1, 2, 3 printing, because we just finished decrementing in the loop above each of the elements in the array. So we started out with 0, 1, 2, 3 in the array. Then in this loop here, we incremented each of the elements. So then we had 1, 2, 3, 4. And then in this loop here, we then decremented each of the elements, so that set them back to 0, 1, 2, 3. So the thing that's actually going to print out in this loop here is going to be 0, 1, 2, 3, followed by a new line. Then in the last loop that we have here, the last for loop, we're using a const reverse iterator. Const because I'm not actually modifying the things inside the loop. I'm not using the iterator inside this loop to modify the thing it refers to, therefore I should make it a const iterator. I'm using a reverse iterator in this case simply because I want to print out the elements in backwards order, so this is a convenient way to do this. So I'm starting out with my iterator here being initialized to cr_begin, which is a const reverse iterator which refers to the first element in the vector in backwards order, which is actually the last element. And I keep going until I hit the end. Each time through the loop I increment the iterator to move on to the next element. And inside the loop all I'm doing is I'm dereferencing the iterator to get the thing it refers to, and I'm printing it out. So this is going to print 3, 2, 1, 0 in the loop because I'm going to print the elements in backwards order from what they are. The current contents of the array is 0, 1, 2, 3, but if I print them in backwards order I get 3, 2, 1, 0. So this is the reason why the last line prints 3, 2, 1, 0. And maybe one other comment I should make is the reason why I'm using a const iterator in this loop here, using cBegin and cEnd. Notice that inside the loop I'm not using the iterator to change the thing the iterator refers to. Therefore, to be safe, I should make it a const iterator. I mean, as a general rule of thumb, when you're using pointers or iterators, if you're not planning to change the thing that the pointer or iterator refers to, for the sake of const correctness, it's always best to make the iterator or pointer a pointer or iterator to something that's constant. On this slide, I have another code example making use of the vector class. And the purpose of this example is just to illustrate a few more member functions that the vector class provides and how these member functions can be used. So if we look at the main function in this example, to begin with, what we do is we create a vector of doubles called values. So this is going to default construct a vector which will create an empty vector. So values initially has no elements in it. Then we have some code here which is really unimportant. And at this point we're going to clear the contents of the vector by calling the clear member function. So the idea is probably this ... code added some stuff to the vector which we now want to get rid of. So we're calling the clear member function to empty out the contents of the vector. So this clear member function will result in values having 0 elements in it after the clear function returns. Then we create a double variable called x, and we're going to keep looping as long as there's no IO errors or other errors, reading in doubles and putting them into the variable x. And then we're going to call the pushback member function for the vector class to take this element x that we've read in and stick it on the end of the vector. Again, pushback basically appends to the end of the vector, adding elements at the end. Then after this loop finally ends, because we've exhausted all the data that we need to read, or some kind of error has occurred, then we print out the number of values that were read. The number of values that were read is how many elements there are in the vector, so we use the size member function of the vector to find out how many elements there are in the vector, and then we print this out. Then down below what we do is we want to count all of the negative elements in the vector. So we initialize our counter to 0, and then each time we find elements that's negative inside the loop, we're going to increment our count variable. So to loop over the elements, rather than use a range-based for loop, because I want to illustrate the use of some additional member functions, I'm going to use cBegin and cEnd and use iterators explicitly in order to iterate over the elements in the vector. So I use cBegin to get an iterator which refers to the very first element in the vector. I'm going to loop, incrementing I each time through the loop until I hit cEnd. And each time through the loop what I'm going to do is I'm going to check to see if the thing the iterator refers to, in other words *I, is less than 0. In other words, is the quantity negative? If it is, I increment my counter, otherwise I don't do anything. And in this loop, the reason why I'm using a const iterator, notice that I'm using cBegin here, not just begin, because inside the loop I'm not using the iterator to change the value of the thing the iterator refers to. In other words, here I'm referring to what the iterator is referencing by dereferencing it with a star operation. Notice that I'm never trying to change *I. So for this reason I use a const iterator just to emphasize in my code I have no intention of changing the thing the iterator refers to. And in general it's probably a good idea when you're using iterators, anytime that you're using an iterator and you're not going to use the iterator to change the thing it refers to, it's better to use a const iterator for the sake of const correctness. And then after the loop terminates I simply print out the count, which is the number of negative elements that I found in the vector. On this slide I have another code example using the vector class. And the purpose of this example is to illustrate the use of Emplace operations. So if we look at the code example in more detail, we have a vector of ints called v. So each element in this vector is actually a whole vector of ints. So the first element is the vector 1, 2, 3. And the second element in this vector is a vector of ints 4, 5, 6. And basically what we want to do here is you want to add to this vector v another vector of ints, in other words, another element. And in particular, we want to add an element which looks like this. It's basically a vector of ints with 10 zeros in it. So there's two ways that we could do this. One is we could use the commented out code that I have here. We could create a vector of 10 zeros. In other words, invoke the constructor for vector int, passing it a parameter. The parameter is 10 and 0, so 10 is the number of elements in the vector. So there's 10 elements. 0 is the value to initialize them to. So this will create a vector of int where there's 10 elements and they're all 0. We can then take this object and we can call pushback in order to copy the contents of this vector into the vector v as an additional element at the end of the vector v. This is inefficient though, because the only reason that we're creating this vector outside the container is solely so that it temporarily exists so that we can copy it into the container. However, in this case, we don't actually need this vector to ever exist outside the container. In this particular example, the only reason that we created this vector here in the first place, this temporary object, is so that we could copy it into the vector and then throw the temporary object away. On the other hand, what we could do is we could say, use the Emplace member function in order to add this vector. And the parameters to Emplace back, what they are, these are parameters for a constructor. So these are parameters for a constructor for vector int. So what this is going to do is this is going to create in place inside the container a vector which is constructed using these parameters. So this will create a vector that consists of 10 zeros inside the container. So the difference between Emplace back and this commented out line of code, in the case of the commented out line of code, we first create a temporary object outside the container that has the data that we want to get inside the container. Then we copy the data inside the container, and after we're done, we throw this temporary object away. In the case of Emplace back, though, instead of having this middleman object where we put stuff that we want in the container into this temporary object outside the container, then copy the temporary object into the container, and then destroy the temporary object, instead we just say, well, let's just create the object directly inside the container, and then we don't have to create any temporary object to begin with. And this is essentially what Emplace back does. It basically creates the new object at the end of the vector in the container without it ever existing outside the container. So this eliminates the need for copying things into the container and possibly having temporary objects as well.